So welcome everybody to the 9th Solar Climate Intervention Virtual Symposium. And so again, we're always looking for new speakers. So if you want to share your research, please reach out to either me or Simone. And so our first speaker today is Daniel Hueholt. Daniel is a PhD candidate in atmospheric science at Colorado State University, and he's co-advised by Elizabeth Barnes and Jim Hell. So Daniel, if you want to share your screen.
Okay, so yeah, just to mention, we have 20 minutes about for talks and then
Great.
10 minutes discussion. Do you want to give a heads up, Matthew? After,
Yeah, sure, I can do that.
If it's going too long. Okay.
Yep.
Cool. Can everyone see my screen?
Yep.
Yep.
That's good.
Great. Thanks for the introduction, Matthew, and thanks for the invitation to speak, Matthew and Simona. Like Matthew said, I'm Daniel Hueholt. I'm a PhD candidate at Colorado State University, and I'm here to talk today about some work I have about ecological risk in future climate change and stratospheric aerosol injection scenarios. And to start off, I just want to talk a little bit about ecological risk, because ecological risk can come from a whole range of different sources. And the one that I'm going to talk about today is about the movement of thermal niches. So in general, species want to stay in the thermal niche to which they are acclimated. So for example, let's say you're a hummingbird that spends the winter in Central America, and then the climate starts to get warmer. Over time, on a population level, the population can shift northward to follow those conditions. And if it continues getting warmer, they could even shift farther northward into the mid-Atlantic, for example. And this is an example of how climate change can redistribute or cause species to move or expand their range if the species are capable of responding quickly enough to the environmental change. But this time, let's imagine that you're a different bird and you live in a boreal forest near the Arctic. In this case, the climate starts getting warmer and you can move a little farther north, but then you hit the edge of the continent and you can't move out over water. You can't become aquatic. So then you are in danger because you can't move to stay in the environmental conditions in which you're acclimated to. And this is how climate change can endanger ecosystems, either around transport barriers or when the rates of change in the climate are so fast that species can't move to keep up with them. And a similar process occurs around topography. You can move up the spatial gradient in temperature towards the top of the mountain where cooler conditions are, but eventually there's no more mountain for you to move up, and then you're in trouble because you are stuck in environmental conditions that you're not acclimated to. So the movement of thermal niches in a changing climate poses risks for a wide range of terrestrial and marine species. And one way that we can efficiently describe this movement of thermal niches is through a parameter called the climate velocity of 2-meter temperature. So this is calculated just as the local warming rate in temperature, the local change in temperature, divided by the local spatial gradient of temperature. And just by unit analysis, that gives you a space per time, which is just a velocity. So this yields a vector that has a magnitude and a direction. And here we're going to focus on analyzing just the magnitude, which we call the climate speed. And from the ecology literature, climate speeds that are greater than about 1 or 2 kilometers per year on land or 7 kilometers per year in the ocean are a problem that's greater than species can adapt to easily. And if you're beyond 10 kilometers per year, that's a really big problem, no matter if you're in the land or in the ocean. Climate velocities or climate speeds are a metric that's most suited to work with linear change on a timescale that's greater than or equal to 10 years. And analysis of climate speeds shows that this is already affecting ecosystems globally. And the examples from that introduction are actually based on things that have already happened in the recent past. And climate speeds in the future are expected to redistribute and endanger species under all future shared socioeconomic pathways. So worsening climate risks such as these motivates research into climate intervention. And stratospheric aerosol injection, or SAI for short, is a hypothetical approach to reduce global temperature by emitting reflective particles into the upper atmosphere, like happens naturally after large volcanic eruptions. SAI is not a substitute for decarbonization. It's really important to be clear about that, but it could complement its goals. And I want to talk a little bit more about how SAI might complement decarbonization. And a couple of framings that are really commonly used are an SAI scenario where you would maintain global temperatures, or an SAI scenario where you would reduce global temperatures. And I want to highlight the second one, where you're using SAI to rapidly reduce global temperatures, partly to connect this to a recent UN Environmental Program report that framed this kind of concept of SAI to reduce temperatures as a potential way where the deployment of climate intervention might be able to alleviate some climate damages within a few years. So how do these SAI scenarios fit into a climate speed framework around rapid rates of temperature change? Well, SAI could maintain temperatures, and you could assume that if SAI is maintaining global temperature, that means, by definition, global temperature isn't changing very quickly. But SAI also add an additional potential dimension of rapid change at either the deployment or the termination of an intervention. And this is where some previous work has been in this space. So previous work has really emphasized the termination piece. For example, in this work by Trizos et al. From 2018, they use a scenario called G4 that features a small cooling at the start of the intervention, and then a very rapid warming when the intervention is shut off while masking a much higher radiative equilibrium. And this work highlighted that there's a serious potential threat from these rapid climate speeds. You can see how red means bad on this figure. And you can see that there's a lot of red everywhere. Some of these climate speeds are 50, 100 kilometers per year. That's much, much larger than the values we talked about earlier. And this work also highlighted that there were potential impacts from that rapid cooling at the start, but they spent more time talking about the termination piece because, well, compare these figures. You could see that the termination is much more dramatic than the deployment in this scenario. So this leaves the question, what specific strategic design choices lead to harmful climate speeds following the deployment of SAI? So to investigate these questions, we use a set of new simulations called ARISE SAI for short that are designed to connect climate outcomes in the simulations to specific strategic design decisions in the scenario. So ARISE 1.5 is a scenario where starting in 2035, SAI is deployed to maintain global temperature at about 1.5 degrees Celsius above pre-industrial. And then ARISE delayed start is a similar scenario, but it starts 10 years later. So because of the warming that has occurred in the meantime, you have to return global mean temperature to the target value, which in this case is 1.37 Celsius, just a little bit lower than that 1.5 value. And then SSP2 4.5 serves as a no SAI climate change control of a moderate mitigation scenario, policy relevant moderate mitigation scenario similar to current committed policies for climate action. And then for an additional baseline, we use the CSM2 last millennium simulation, which is a simulation of the 1,000 years prior to the conventional start of the pre-industrial revolution. And this provides a baseline of the sorts of climate changes that ecosystems might be adapted to in the absence of rapid anthropogenic climate change. All of these simulations are in the Community Earth System model with whole atmosphere community climate model, CSM2 WACM 6. And the SAI simulations use a control algorithm at off-equatorial locations to manage multiple climate targets. And I'm happy to take questions about the setup of these scenarios, which we didn't run. We used this existing output, but I can take any questions about this later. But the key point for the talk today is that ARISE 1.5 maintains temperature, and ARISE delayed start is very similar, but it begins 10 years later. So here we're able to connect differences in the ecological risk in these scenarios to this strategic design choice. So to start off, let's just set some intuition by talking about climate speeds during the last millennium. So these figures are for the land and ocean of the mean of 10 to 20-year periods matching the ARISE ensemble size of the last millennium. And what you can see here is that climate speeds are quite small everywhere. Internal variability, natural forcings, and the anthropogenic changes to, for instance, land use are present, but they evolve slowly during this period. But they're non-zero. Climate is always a key driver of ecosystem variability. And so you do see some non-zero climate speeds. And then climate speeds in a rise 1.5, the SAI scenario where temperature is maintained, are also small. In fact, the climate speeds over land are very similar in magnitude to the last millennium. And over the ocean, you do see a small negative forcing overall because that 2035 deployment year is slightly above the temperature target. So you still bring down temperatures just a little bit to reach that target. But overall, a rise 1.5 looks pretty similar to that last millennium simulation. In SSP2 4.5, the no SAI moderate mitigation future scenario, climate speeds are large nearly globally, and they're positive in sign, meaning that they're forced by warming. And the largest climate speeds are seen in the tropics, particularly the tropical ocean, where the spatial gradient is small, so you have to move a large distance to keep up with even a small change in temperature. And then the climate speeds are also high in the Arctic because the warming rate is highest there. And this lines up with picture from the ecology literature of where ecosystem risk is the greatest. And this feature in the North Atlantic is the North Atlantic warming hole, where temperatures are cooling because of a slowdown in the Atlantic meridional overturning circulation within the ocean in these simulations. Now, in the delayed start scenario, climate speeds are also large, and they're negative in sign globally because they're forced by this rapid temperature reduction to compensate for the warming that occurred during the 10-year delay. And the magnitudes are actually as large or larger than SSP2 4.5 with no SAI at all. And there's potentially dangerous climate speeds over more than 2/3 of the land area. So climate variability still plays an important role in the presence of the forcing from SAI. So each of these dots represents a value of median climate speed in an ensemble member or a 20-year period of these simulations. And if the dots are solid, they're exceeding the threshold of potentially dangerous climate speeds for the land or for the ocean. And if they're open, then they're below those thresholds. And what we can see is that while there is spread here, a rise 1.5 is actually statistically indistinguishable from the last millennium on this planetary scale, but there's no overlap between a rise delayed start and a rise 1.5 or the last millennium. If you compare the minimum member in delayed start over land and over the ocean, it's greater than the maximum member in a rise 1.5 or the last millennium. So this is a very large difference in the global climate speeds from predominantly this 10-year delay in the scenario design. So climate speeds provide one way for us to think about relative risk between future scenarios. So this is a figure where the x-axis is the rate of temperature change per year, and the y-axis is the global area that's exposed to climate speed beyond 10 kilometers per year. And 10 kilometers per year from, as we said earlier, that's a threshold of really extreme risk no matter anywhere that you are. So this figure is showing the global area that's exposed to a very large climate speed. The last millennium, as you would expect, is near the 0 point on this figure because natural forcings, anthropogenic influences evolve slowly over this period. So climate is generally, when it's changing, is changing very slowly. And the maximum in that last millennium variability is given by this dashed gray line here at about 10% area exposed. And this is for all 20-year periods in the last millennium. So scenarios of future climate change and representations of the recent historical period cluster above that line of last millennium variability on the right side of the figure, showing that these are coming from warming. And just some things to highlight here is that the area exposed to these climate speeds scales pretty much like you'd expect. The less mitigation you do, the worse the global ecological risk is. So RCP 8.5, which is a no mitigation scenario, lies all the way up here, whereas SSP 2.6, which is an extremely aggressive mitigation scenario with very rapid reductions in mitigations very shortly, is still above that last millennium variability, but it's much lower. Over the recent historical period, the ERA5, which is an observationally constrained representation of historical conditions, lies still above SSP 2.6, whereas the CSM2 historical is a little higher because CSM2 warms too rapidly over this period. But overall, this is consistent with a picture of ecosystem risk in the recent past, and then our choices about mitigation in the future, determining the relative level of ecological risk in the future. Scenarios of stratospheric aerosol injection that cause rapid temperature reduction cluster above that last millennium variability on the left side of the figure, showing that this risk is coming from rapid cooling. And the important thing to look at here is that because of how these ARISE scenarios are set up, we can actually connect the rapid temperature reduction to specific strategic choices. So in this top one, which is done in the UK Earth system model, here you overshoot the target before your deployment because of the high climate sensitivity in the model. So because of this, you have to rapidly reduce temperatures to reach that 1.5 threshold. In this scenario, ARISE 1.0, you're intentionally choosing a low temperature target at the time of deployment. So you're trying to rapidly reduce temperatures deliberately, and indeed, you get a rapid temperature reduction with its associated ecological risks relative to the no SAI control. And finally, in the delayed start scenario that we've been focused on mostly today, you selected your temperature target, about 1.5 Celsius, but then delayed deployment until that target had been until temperatures overshoot that target, and then have to rapidly reduce temperature to reach that target. And regardless of the underlying strategic logic, the really important point here is that in all of these rapid temperature reduction scenarios, you're increasing the area exposed to these extreme climate speeds relative to not doing SAI at all. Finally, the scenarios of SAI where temperature is maintained, like ARISE 1.5, the one we've talked about earlier, and a similar scenario called GLENS, these actually fall within last millennium variability in the ensemble mean. These are actually the only data sets that we look at where you actually stay within that last millennium variability. So in this case, you're really getting rid of those most extreme global risks from climate speeds in particular. But the biggest difference between that ARISE 1.5 and that ARISE delayed start scenario is that 10-year delay. And this is really illustrating how a seemingly small change in the strategic logic leads to a very large change in the profile of global ecological risk. At a very high level, this is all coming from the global temperature trends. So this is a figure of just global annual mean temperature time series. Orange is the SSP2 4.5. Teal is that ARISE 1.5 maintaining temperature, and then purple is the delayed start, where you have to rapidly reduce temperatures. And essentially what we're saying here is that if this is a problem, because that's climate change, and we know climate change comes with severe ecological risk, then on this one specific metric, maybe ARISE 1.5 might not be so bad because you're maintaining temperature. But the delayed start is also probably a problem when you have to rapidly reduce temperatures to reach a target. When the change in temperature, the rate of change in temperature is what you care about, it really matters whether you're rapidly changing temperature, whether that's from climate change or from a theoretical climate intervention scenario. And a couple of scenarios that you could imagine that would avoid this rapid temperature reduction or deployment shock would be a delayed start maintenance scenario. So here you are deploying after 2035, but you're also raising the temperature target. So you're just maintaining temperature at that value, no matter what it is. Or another possibility would be a slow start, where you modulate the start and make sure that your climate speeds are never that large. And I think David is actually going to talk about this in his talk, so that dovetails really nicely. So in summary, the ARISE simulations allow for outcomes in different scenarios to be connected to specific strategic decisions. Climate speeds when global mean temperature is maintained with SAI, like in the ARISE 1.5 scenario, are similar to those experienced over the last millennium. A similar SAI strategy, but with deployment delayed by 10 years, like ARISE delayed start, yields large planetary scale climate speeds. And these climate speeds during the ARISE delayed start simulation are far beyond the last millennium variability, and they're greater than climate change without SAI at all. And avoiding potentially dangerous climate speeds can help inform future scenario design if we are thinking about making sure that climate speeds are never too large. That maybe limits what temperature targets we can use at what time in designing these scenarios. And with that, thank you for listening, and I'm happy to take questions. There's a preprint of this work, but a revised version of this work, which is a little different than what you'll see in the preprint has been accepted at Nature Communications and should be online soon. So yeah, I'm happy to take any questions at this time.
Thank you, Daniel. That was great and perfectly timed. So that's very good. So I think if you have any questions, please put them in the chat or raise your hands. I see Alan has his hand raised, so please go ahead.
Hi. Yes, we did all this in Trissos et al. And we also looked at precipitation velocities. And ecological niches are not defined just by temperature, because and we showed that in some cases you have to go one direction for temperature and the other direction for precipitation. So I was just wondering what's really new here, and why aren't you also including precipitation?
Thank you for that question, Alan. Yeah, so you can define a climate velocity for any variable. And another one that people often find of interest is to look at the climate velocity of precipitation. And yeah, in Trissos et al., it was shown that sometimes those move in opposite directions, and that can be very important for ecosystems. And yeah, it's absolutely true. There's way more to ecological risk than what we're looking at here. But for this study, what we were trying to look at was ARISE for the first time let us connect the outcomes to this very concrete change in the strategic logic of a 10-year delay. And for that story, we felt that the climate speed of temperature, and the reviewers seemed to also agree with us that the climate speed of temperature was sufficient to really illustrate that work. So I think looking at the climate velocities of other variables would be a great avenue for future research, but lay outside the scope of what we were trying to do here. Thank you.
Sorry, Hongwei, please go ahead.
Okay, thank you, Daniel. Very good talk. I have a question about, so based on our results, it seems like SAI can decrease temperature, but may like increase climate speed. So I'm curious, like if we do like decreasing temperature by just reducing CO2, how would the result like? Would reducing CO2 also like increase climate speed? Just curious.
Yeah, so thanks. Great question. And yeah, we think that this is intrinsic to the ability to rapidly change temperature. So by definition, if you're rapidly changing temperature, you're rapidly changing temperature, regardless of the reason for that. So regardless of the intervention method you're using, this is going to happen when you rapidly reduce temperature. You're going to get these large climate speeds. SAI provides a nice illustration of that because there are these Earth system modeling simulations of it. And also because, as mentioned in the UN report, I mentioned SAI is the only way we know that you could rapidly change temperature with near future technology. But yeah, if you, regardless of the method, some very hypothetical, extremely rapid method of carbon removal or space mirrors or whatever, then yeah, like rapidly reducing temperature is always going to have this risk associated with it.
Thank you.
Thanks. Any other questions for Daniel? Oh, Michael Diamond, do you want to turn on the mic, or shall I read?
Hey, Daniel, really nice talk. Do you analyze the direction component of the climate velocity vector at all? I really like your hummingbird versus songbird example at the intro, and I was wondering if you did anything with that in terms of the analysis.
Yeah, so I think that would be definitely something that somebody could do in the future. We felt that with the resolution of the data we were looking at, we felt that getting into questions about how is the direction changing in different regions, we didn't feel confident in that kind of analysis here just because of the coarse resolution of these global data sets. But were somebody to look at this with much more fine resolution and try to tie that to specific, really granular questions about what's happening with direction in what region, what's happening for individual species, that would be a really interesting direction for future analysis. But we think that would require more fine scale data than we had here with these simulations. Because to get at that, you have to be really confident that the spatial gradients you're looking at are really representative of what species are experiencing. And for a global analysis like that, we felt that this was the right tool for the job, but getting at more granular questions about regions and species, I think you would want finer resolution data than we had here.
Great. Any other questions? I have a very small question, if not. Yeah, did you think about using data from marine cloud brightening simulations to look at similar things? And would you expect the results to be different?
That data definitely wasn't available when we were starting this work for that. So that was one reason. But I do think that, again, just for what we were trying to do here, tie this into the strategic logic of the 10-year delay in the SAI simulations, bringing in a different intervention method would, I think, have been outside of that. But yeah, you could run this analysis for those simulations.
Great. Okay, I think we'll move on to the next speaker. Thank you very much, Daniel. That was great.
Thanks.
Simone, do you want to take over?
Yeah, sure. Okay, so thanks again, Danielle. And now we have David Heath from University of Chicago. David is the professor and founding faculty director of the Climate System Engineering Initiative and is talking about solar geoengineering. Oh, yeah, could start soon if it is small. David, please go ahead. If you have, do you have slides to share?
Yeah, I have just a couple slides, Simone. Thank you very much. So first of all, thanks a lot, Simone and Matthew, for the invite. And thank you very much to Wake Smith, my collaborator on the paper I'll talk about, and also to David Verbart and Frank Koich, who are collaborators on a kind of separate linked set of work on atmospheric chemistry, which I'll say a little bit about. So I'll just show some very simple slide of outline. So talk title, and here's the way I'm going to divide up this pretty non-technical and short talk. I'm really looking forward to conversation and questions. So I'm going to say a little bit about what subscale deployment might be, why, that is some potential motivations for a deployer to do subscale deployment, who, what are some what are examples of potential coalitions of deployers, or what would be the structure of who might do the deployment, and then some technical methods about how it might get done. So, first of all, what do we mean by subscale deployment? To me, that means something that is, first of all, deployment. This is not an experiment. It's something that is deployment, but a deployment at a fraction of the full scale, where, often when one thinks of subscale models in engineering and other fields, you think of things that are sort of at a tenth or a third or something like that of full scale. So some kind of potential things that would set the scale are, one is something that roughly perturbs by a factor of 2, let's say, the background flux of sulfur into the stratosphere. So that's this number that's of order 100 kilotons sulfur per year. So that would alter the stratospheric sulfur concentration, alter the aerosol distribution in a way that was quite significant, but still quite small on a climate scale. Another way to think about what subscale is that it's big enough to be a meaningful fraction of some ramped deployment over a decade. And I'll get to what that means. And another possible definition of subscale is that it is, say, as big as the radiative forcing net increase we effectively had from the International Maritime Organization restriction on sulfur from marine diesels. So those are some examples of what subscale could mean, but I think there's a whole lot. Wake and I definitely don't think we've got an inclusive set. The idea from our point of view, the reason to write this paper is to get people thinking about the fact that there's a range of these subscale deployments that are possible. Now, of course, the middle of those I mentioned was something that was a fraction of a ramp, but what ramp? So that gets to what, the definition of what subscale is depends on what your opinion about what full scale is. And there's a huge range of opinions, and nobody knows is, I think, the bottom line answer. So obviously, starting from the largest, one potential kind of deployment of solar geoengineering is to drive temperatures down quickly in, say, a decade or so. My view is it's actually pretty hard to argue that that makes sense on a risk management grounds, but it's not impossible. And obviously things that don't make sense still get done. So it's possible. But Daniel's talk before this just set out some of the obvious risks of rapid cooling. Then there's this idea of stopping warming. A bunch of the previous talk was framed around the idea of waiting a while, but then still coming back to 1.5. I do want to point out 1.5 is a political target, not a scientific target. It's a political target that was made without reference to SAI. So I think, while it might be that it's a sticky target and for some reason people choose it, there's no sort of scientific rationale for 1.5 in that sense. And in a world with SAI, you can think of a lot of different risk trade-offs. Beyond that, there's an idea of SAI to half the rate of warming, that's to cut the rate of warming in half, or to cut it by less than half, say a third, which still cuts some risk terms, the rate of growth of some risk terms, by something that might be more like half. So, for example, as several papers have demonstrated, the reduction in the intensity of tropical cyclones responds roughly twice as fast as the temperature to SAI, so that SAI that cuts temperatures in half, cuts the energy in tropical cyclones, brings them roughly back to pre-industrial. So that means that a ramped deployment that, say, stopped the increase in tropical cyclone intensity on average, forgetting, of course, all the hard science about where these cyclones actually are, such a thing would be equivalent to about cutting the rate of temperature growth by a third. So that's a kind of range of potential what full scale is, and then subscale some fraction of that. Give you a sense of what these things actually might look like in scale from a figure that was in the paper Wake and I wrote, or in the supplemental appendix. This shows you in millions of tons S per year on the x-axis, and time on the y-axis, obviously millions of tons S per year on the x-axis. Y-axis gives you some sense of what these things might look like. This, to be clear, is sulfur flow, not radiative forcing. In the paper that Wake and I were contemplating, we're talking about injection at 15.5 kilometers in the extratropics, and that would have significantly less radiative forcing per unit sulfur. We don't know exactly how much less. But in terms of sulfur amounts, that scale we were talking about, that 100,000 tons a year, is a scale that is equivalent to half a decade or say of growth of something that would be a half warming ramp. And so that gets back to the kind of definition of what a subscale might mean. So that's kind of a summary of what it might mean. Then I'll say a little bit about the next question, which is why. What might be the motivation of some deployer, and we'll get to who deployers are and the who. What might be the motivation of some deployers to do this? So I think the first and kind of most obvious is that if some deployers have a reason to judge that SRM deployment is likely to be beneficial, so they've convinced themselves from the science that full deployment, or one of these versions of full deployment of SRM, would meaningfully reduce risks and be in the interests of the deployers, then a reason to do subscale deployment might be to open up political and technical pathways to deployment. Obviously, subscale deployment doesn't necessarily do that. You can imagine that it backfires politically and closes off political pathways to deployment. But I think both are possible, and we're just talking about potential motivations. Another possible motivation, so one is that basically, to be blunt, the slippery slope, the idea that doing this at a small scale and assuming that there's no dramatic surprises might substantially reduce concerns about doing a larger scale, and might allow a coalition to develop for larger scale deployment. And that would be in the interest of deployers who were convinced that solar geoengineering would reduce risks that mattered to them. A second possible motivation is that you would actually be able to claim some reduction in risk. So even these quite small subscale deployments, they wouldn't produce a perceptible to a regular person change in climate, but to be clear, actually even full-scale deployment wouldn't do that on a short time scale. But you could, using the kind of attribution methods that are now used for extreme events in climate, you could, with these subscale deployments, make some claim that you were incrementally reducing the rate of growth of some risk. And that claim might or might not be politically useful to you, but it would objectively be actually doing some small thing for risk reduction. That's exactly the flip side of the talk we've heard about the additional climate risk that came from the IMO stopping sulfur in marine shipping. Then the third category, so first category was opening up the pathway, second category was some kind of claim of benefit. The third category would be knowledge, would be that actually if you perturb the flow of sulfur in the stratosphere by a factor of 2, you learn a lot about stratospheric circulation, about aerosol size distribution, about at least some of the chemical side effects, perhaps there's some side effects related to upper troposphere. So it's a fair amount that you could learn if you did the deployment and serious monitoring and science to go with it. That's crucial. Finally, one last kind of related version of why is deployments in this kind of subscale category are deployments, I believe, but they're deployments that arguably would not violate the significant transboundary harm provision, which is the sort of underlying customary international law provision about what states can do without some international agreement. And so you could argue, obviously there could be counter arguments, but you could argue the deployments of this time of this scale did not require some, or did not violate that crucial provision of international law. Okay, so I've done what, I've done why, I deal with who. So I think the big answer is we have no idea. I think there's, if you step way back, I'm talking to a bunch of people, I assume, many of whose names I can see and know, who spend a lot of their days thinking about these topics. But very few kind of practical political leaders have grappled, few if any, practically with the reality of deployment of SRM. And I think until that happens, speculations by folks like us just don't mean much. I think we really don't know which sorts of countries would do this, in what way, for what coalitions. It's extremely hard to guess. I think we can make one general statement, but not even with very high confidence. The general statement is that it's more likely to be a coalition than a single country. I think the reason for that is, even if you imagine yourself, you're a single country and you are rationally self-interested and rationally convince yourself that SAI deployment was to your benefit, not because of any wonderful belief in human unity, but simply out of rational self-interest, you'll know that if you act alone, there will be more likely to be counter pressures that will tend to stop the deployment than if you act in some coalition. So there will be a rational reason to build a small coalition. I think that's likely the way it happens. And we think there are no perfect analogs. When we think of things that are at least partial analogs to this, I think small deployments, small coalitions is likely the way it goes. I don't know how much more than say that. You can easily name a whole bunch of countries, but we just have no idea what the actual distribution of countries will be. So then I'm going to flip to the last topic, which is how. So I've got with what, why, who. I didn't really say much, but I said what all I think we can usefully say. And then the last question is how. So this reiterates a little bit of what's in the paper that Wake and I wrote, with a few added things. So one of the insights from that paper is that that existing aircraft, like business jets of this G650 class, basically the key thing to remember is that one of those jets operating from an airbase with an operational system behind it can loft something like 10,000 tons per year to an altitude of 15.5 kilometers. The big question is, if you're doing this in the mid-latitudes, what is the radiative forcing efficacy, the amount of radiative forcing or cooling you get? It's not quite the same because, of course, radiative forcing, because, of course, the cooling efficiency of radiative forcing itself has a latitudinal dependence. But what is the cooling or radiative forcing efficacy you get for that? And in our paper, we casually guessed that it was about a third of a more conventional high altitude deployment, but that is a guess. It might be incorrect. But that number about the amount of lofted material is a relatively robust number. Second, we did not resolve the question of what actually would get lofted. So that ties into separate work that Wake and I are pursuing, along with Dave Verbart, Frank Voigt, and others. But I'd say the convention in this field has been to assume that a lofted quantity would be SO2. But of course, there are other options. You can loft S and burn it in situ. You can loft H2S, and H2S and SO2 would both be lofted as chilled liquids. I think the obvious way to do it would be as chilled liquids. H2S has a higher vapor pressure, so it's even easier to release once you're in the stratosphere. It has roughly half the weight of SO2, so you can get roughly twice as much sulfur for a given aircraft deployment system. Dave Verbart has done these initial calculations so far on the oxidation of H2S in the stratosphere, and we find that it goes to SO2, and it goes to SO2 faster than SO2 oxidizes onto SO3. So it looks like in that sense, it would be about the same as SO2. What we have not yet looked at is, of course, you're putting an extra mole of water in there, and the oxidation of SO2 depends on the local water vapor concentration quite strongly. So it's conceivable it actually ends up being faster. We just, I think, don't know at this point. Wake and I contracted with a safety sulfur safety consultant, and my read of that report and other materials is that H2S and SO2 in the kind of chilled liquid forms have kind of roughly comparable operational risks. H2S is not significantly more risky. It's more risky in some respects. That's the way I read it. And so in that sense, there wouldn't be much of a trade-off. And what that says to me is there's a good chance that people would use something that was more non-sufficient than SO2, something like H2S. We looked at some other things, including carbon disulfide, which to me looks a lot less plausible now, both for reasons of the reaction chain in the stratosphere and the dispersion of particles in the stratosphere and the production of it. So I think it's a less likely outcome. And I'm happy to answer some questions about aircraft and aircraft fleets, and Wake, my co-authors, also on board. So just stepping back in conclusion, I'm looking forward to Q&A on this, which I think is the most relevant thing. I'd say, what's the point of this? I think the point of this is to encourage this community to analyze scenarios that include some kind of subscale deployment, because it's, I think, quite plausible that some version of subscale would be the way these things start. Lots of other things and kinds of perturbations or interventions of the world start with some subscale system. I think there's the practical fact that some version of this can be done with existing aircraft, but there's also a bunch of reasons why a subscale, that is a subscale that's continued for some length of time, but then decision points after that about stopping or ramping up is in fact a kind of plausible thing to do. So what kind of analysis is needed? I think what's not needed so much is GCM runs, where it's actually hard to get enough signal to noise for these very small amounts of SO2 to see much. But I think what is useful is some work on particle size distribution and related atmospheric chemistry. A big question that has not been resolved by this community is that if you're releasing any of these compounds in the wake of an aircraft, you get locally high concentrations for a long time in the aircraft wake, and that will depress the OH concentrations, which changes the reaction rates, and that's not been studied enough. The altitude dependence of injection for these small deployments hasn't been studied enough, so those are both things that I think could be effectively done, as well as studies of detectability and impacts. Thanks very much. Look forward to hearing questions.
Okay, thank you, David. Great overview, summary, and giving us the nice overview. So yeah, we already have some questions in the chat, and there's also a hand up. So I think I'll start with Mike. He had the first question. And Mike, do you want to unmute yourself, or do you want me to read it?
Oh, okay. David, I guess I'm wondering if you have any thoughts about the issue of acceleration of sea level rise and trying to focus some of these early simulations on trying to get at polar regions and prevent the rate of sea level rise from increasing so much.
I have been more involved in that at Chicago. As some of you know, we ran a whole workshop on cryospheric interventions. Certainly these quite small subscale deployments, I think, would not have much effect on cryosphere, but it has some effect because, of course, there's this very strong summertime peak to surface melting. So if surface melting is a concern, there's at least some effect. Of course, for marine ice sheet instability, which is more driven by the warm water mass, the effect of these things would, I think, be very small. I will comment that I think sea level rise is obviously one of the many climate impacts that matter, but I want to reiterate the fact that there's now really abundant evidence from the impacts community that the climate impact that drives most of the total climate impact is simply temperature on mortality and productivity. And that is overwhelmingly focused in hot countries. And that's the thing that we're most confident SAO can directly address.
If I can just say one more thing, I've been wondering if cirrus cloud thinning in the winter might actually be something to particularly apply to trying to cool ice sheets. So it really helps cool down the ice sheets and would make them potentially less susceptible to summertime high temperatures. And that might have been why in the sort of Holocene optimum or something, when you actually had a fair amount of extra summer heat, you perhaps got enough winter cooling that didn't lead to huge amounts of sea level rise.
That's possible. I think we don't know enough about what fraction of cirrus clouds are now homogeneously nucleated. I think there's lots we don't know, but I think it's worth looking at it for sure.
Okay, thank you. Thanks, Mike. Next is Eva. You want to unmute yourself?
Hi, David. Thank you for a nice
Hi.
talk. I was wondering, you spoke about H2S as a possible substitute for SO2, and you said that according to like sulfur liquid representative, does not really, using H2S as a substitute of SO2 does not really increase risks associated with the deployment. But like H2S is highly toxic, right? And I kind of find it hard to believe that using H2S like a very toxic substance, spraying it in the stratosphere and does not increase risks. Can you comment on that? I mean, I guess the assumption is that...
Yes, I can. And maybe especially as an Albertan, I've actually worked in my former department and at many places not very far from me here, there's industrial H2S at large quantities. So I think the answer is it is highly toxic, but so is SO2. So the ratio, there's different numbers for the ratio. So you can look at both the lethal dose, the LD50 numbers for kind of acute toxicity. And for them, there's about a factor of order 3 between the two.
Okay.
So it's not that big a number. Because SO2 is a quicker acting acid, there's some respects in which it's more dangerous, but other respects in which H2S is more dangerous. But I think the point is if you're talking about a risk to operators, where you have a large compressed gas facility for H2S or SO2, if you go to talk to people who actually work on sulfur safety on a routine basis, and I'm in Alberta right now, there's a lot of sulfur gas plants that deal with these chemicals routinely, they don't look at the risk as being too different in the sense that for either compressed SO2 or H2S, if you have a leak from a pressure vessel or a leak of these chilled liquids, the risk to anybody standing right there for a material leak is acute, extremely acute. And the factor of 2 or 3 difference doesn't make much difference. That safety consultant used very standard industry methods to calculate the radius of acute risk from a crash that breaks a whole aircraft apart. And that radius is like 4 miles under particular wind conditions and so on for SO2 and 4.25 miles for H2S, which I think is, given the scale of that risk, really not that significant. H2S does have a flammability risk that SO2 doesn't because it burns, but that flammability risk or associated explosion risks, when you look at them in terms of radius and using kind of standard industry calculations of risks, are much, much smaller than the toxicity risk. So basically for big accidents, you'd be killed from either one by the toxicity in general before the flammability risk from H2S, which is, to be clear, no bigger than natural gas risk, would be significant.
And what about just releasing it in the stratosphere? I guess the assumption is that by the time it comes back to the troposphere, all the H2S is basically gonna transform into another less toxic compound. But is there still gonna be like a fraction that comes down to the troposphere in the H2S form?
So this is where we need to do some real abstract chemical modeling. We're not saying we have all the answers. So we've done the preliminary obvious calculations about reaction rates. And the reaction rates for H2S to SO2, which is the first step of that chain, are much faster than SO2 to SO3.
Yeah.
That makes it seem very unlikely there'd be a significant aspect, and that's true in the stratosphere. In the upper troposphere, there's more water vapor. The reaction rates would be, I think, even faster, but that's something we haven't looked at.
Okay, awesome. Thank you.
But I think the big thing I would point out is that I think many people have the idea that H2S is much more toxic than SO2. But I think if you go talk to people who practically deal with these compounds in industrial facilities, they don't say the risks are that different.
Okay, good to know. Thank you.
Okay, I'm not sure if Wade wanted to add anything on that, but else, Andrew has the same thought. Andrew Lockley, do you want to unmute yourself?
Yeah, I just wanted really to draw people's attention to a few items that I put in the chat that I think might help support the debate. So, David, you're talking about mid-latitude deployments. There's been a paper that came out in the last couple of days in Earth System Dynamics, I think, looking at the link. I've sent a link to that. It's quite supportive in suggesting that deployments up to 60 degrees north might still be, quite, acceptably efficient. Although on some metrics, the ones at 30 degrees north are more efficient. I didn't quite get the difference between the two, so someone else might want to comment if they've got a clear understanding of the difference between those two metrics. The other thing to point out is that, David, your own paper, a temporary moderate paper, which I think was co-authored with Pete Irvin, was
No, with Doug.
similar. That was Doug, right? Okay.
Yeah.
That was looking at a deployment which is perhaps not wholly dissimilar from the one that you're envisaging, although the ramping rate might be somewhat different. I noticed that you've chosen a linear ramping rate as opposed to, say, for example, a logistic curve, which is something that you might perhaps want to comment on. The final resource I put in the chat is a chap called Thomas Pueo, I think is the name, and he had a debate yesterday with Danielle Visioni. He's trying to sort of do kind of this thing, amping make sunsets and getting them to be the deploying agent. And obviously people have got fairly strong opinions about make sunsets, how serious they are, and whether their balloon deployment system is credible or safe at scale. But I think it's worth at least looking at the fact that people are, making what some might argue are increasingly serious attempts to scale up these micro deployments, so they sort of get onto the bottom of your little ramp that you've drawn there. And I just wondered if you might want to comment on any or none or all of those resources.
Not much comment to offer. I guess I'd say I've talked with the folks at Make Sunsets for a long time, since before they were public about it, and I do not believe that. I believe that they are being effective at raising the topic as a kind of a stunt or theater, which is why you're talking about it and we're not talking about it. And what long-term impact that has as theater is hard to know. I do not get a sense that they have any realistic pathway even to subscale deployment.
Okay, good. I would have a question, if that's okay, answers the question. So
actually, I want to continue on that. And I think the point is lots of actors, be they things like Make Sunsets or many people on this chat or environmental groups or different UN agencies, will affect the way this is talked about and the way actions work. So I think Make Sunsets has a role in the conversation for sure. But I think it is very likely true that if deployments happen, even at this kind of subscale that Wake and I talked about, that they're fundamentally under the control of states. There's a way in which even if some non-state actors would start to do this, there are forces that would make it very quickly become de facto a state action, in a sense that if it's happening under some state's purview or in their territory, that state really has a choice of either shutting the thing down or of making it a state action. So I think not that states are everything, because non-governmental organizations and transnational organizations are very important, including some of these UN agencies and environmental groups and so on. But I think there's a way in which deployment like this really looks like a state action pretty quick.
Just as a short corollary on that, I know that there are plans to use carriers, not full-scale aircraft carriers, but just small boats to launch the balloons that take them outside into international waters. That's been discussed actively.
Well, if there's really plans like that are published, that are scaled, that don't have ridiculous environmental impacts or costs, I'd be interested to see them. I have not seen them.
Okay, yeah, so I still have a question regarding a little bit the timing or the feasibility when this could happen. You addressed most of the other things. So my question is in both the technical as well as the political. What conditions would we need to have something work fairly quickly? We're talking obviously about soon deployment. So, and maybe also to Wake in terms of the technical potential, if you can comment.
So if you're talking about the technical potential to do it with those existing aircraft, in this kind of order of 10 aircraft, where you also need the supply chain for the material, that depends on the level of effort and sort of a state doing it and financial backing. But I think if you think about other things that are not politicized, which I'm not saying it shouldn't be politicized, it should be politicized, but other things that are kind of like similar scale activities in terms of money and flows of materials, I think doing that, building up a capability to do it in something like 5 years is not unreasonable at all.
Yeah, and then the political, what governance or what system would we need that becomes feasible? And I think I have a third question.
So that's a question that you keep hearing from this community, and it's just not in the language that we use in international affairs. There isn't an answer to what we need. That's just not the way international affairs works. So I think the issue is, which is really unguessable, I don't have an answer to, is at what point does some countries want to do this, which could be never and could be quite quickly, we don't know. But as a matter of, if you accept the argument I gave that there would at least be a strong argument that this was under the significant transboundary harm principle, then states could simply do it. But they don't need any permission. Obviously, many people, including me, would like to see some kind of more global, truly democratic, consensual governance, but that's not how things like this actually tend to happen.
Okay, that makes sense. The last question I also had was, do you see the need for other, like observing system or other things being in place before this is? Do we have enough? Could we start now? What else would we need? What do we miss still? It's technical, it's political, but then are there other things that are important?
Again, I think need kind of implies there's an objective right answer, and I don't think there is. So if you ask me, I would like to have a much larger scientific effort to understand SRM. I'm not advocating a subscale deployment. If you ask me what I'd like to see like a 100 million a year or larger budget that was a broad budget for understanding a whole bunch of technical questions around solar geoengineering, especially SAI, because that's the thing that is the only thing I think can be kind of technically done in the near term. And just for example, that's observing systems, including the development of or deployment of new satellite observing systems that are relevant, new in situ observing systems with stratosphere, new analysis methods. There's a bunch of work that needs to be done in laboratory studies. There's a huge range. So I'd like to see that range done, but it is not necessary to do that in order for some country to decide they might do this. And one thing that Wake put in our paper, Wake's original text, it's a joint paper, but I think Wake is exactly correct about it, is that while those of us in the scientific community may be persuaded that some risks are retired or better understood by a whole bunch more science papers, there's a way in which regular humans may not care that much. And the fact is, doing a subscale deployment, say at this kind of 100,000 tons a year for 5 years, and having no big visible change in the world and no obvious big side effect may be far more relevant to people's actual decisions about the risk, regular people's, not scientists, than a bunch of science experiments. To be clear, I'm a scientist and I think we'll learn more from science experiments, but you have to think in both ways.
Mm-hmm. Yeah, thanks. Great. We take one more question. It's 11, but I do want to go to Gregory. Mike, sorry, you already asked, so maybe you can communicate later with David. Gregory, you want to ask the last question?
Thank you. Thank you for the talk. I just am frustrated by what I regard as the difference between the way we talk. You just made the case that there's no right answer. But in the case of climate change in general, global warming of CO2, my perception for the longest time is that there's much more willingness to talk about the right answer. In the case of the response to global warming and anthropogenic CO2 introduction, than there is to talk about a right answer in the case of mitigating it by, in particular, SAI. Could you comment?
Well, yes. I think one thing is to say, obviously, it feels a little different now. There's much more, significantly more willingness to talk seriously about SAI or other SRM technologies than there was just a few years ago. And as evidence for that, maybe the most recent evidence is the WCRP Lighthouse activity, this 10-year-long activity to both develop a research plan for climate engineering and to encourage governments to fund that research plan. That's a big deal. Lots of other examples. That's just one. I think that there are a lot of reasons why it might be different now, but one reason that ties back to your question, I think, is the fact that we are now really acting on cutting emissions in a way that we weren't even a few years ago. So I've recalculated the number. I think the right number is that we're now spending about 1.7% of global GDP on clean energy. And that is up dramatically from just a couple of years ago. And it's in the range of what many integrated assessment models say is the right amount to spend in a kind of optimal climate management strategy. And I think that really changes the conversation. I think we're near the peak of emissions. I think the peak of emissions will quite likely happen this decade. And I don't think emissions will fall at the pace that people talk about for 1.5. But I think that for years, the big concern, or one of the big underlying concerns about talking about SRM, was that it will be seen as a distraction from emissions cuts, or it will be seen as something we do instead of emissions cuts. And I think the fact that emissions cuts, not perfectly, not exactly the way I would like it, et cetera, but emissions cuts are really underway. And there's this real prospect that emissions will peak quite soon. I think that is one of the things that makes it more appropriate and more acceptable to talk about things that we would do as a supplement, things we do as well as emissions cuts.
Okay. Well, with that, I would like to thank you again, David, and Daniel as well. Thanks everybody for joining us, and we're planning to see you in April, at April 12th, I think is the next one, right? Okay.
Thanks very much.